All right, today's lecture is going to be on groundwater and aquifers. And we're going to be looking at what water is taking place or where we find the liquid water that we generally drink. So we're looking at freshwater sources and human use. So here's a picture I'm going to refer to several times throughout this lecture. So here we go. Let's first look at how water is distributed. If we look at the distribution of Earth's water, we'd find that 97% are found of ocean water is saline. Right? It's simply briny. It's got salt in it. And that's not really relevant to us here. We're going to look at just freshwater, which represents or comprises about 3% of the total water on Earth. If we break down the percentage of freshwater, we would find that ice caps and glaciers contain about 69% of all the remaining water. Groundwater contains, let's just say, about 30% of the remaining of the 3% freshwater. And surface water is really just a fraction of a percentage. We're really talking a tiny amount. So, surface water. When we look at what surface water is comprised of, we're talking about lakes and swamps and rivers. We're talking about the water we would see at the surface. So, the tiny amount of water that's on the surface, actually most of the water is in the liquid form, right? Not the ice caps and glaciers, is groundwater. So, there's so much more water just beneath the surface. So, groundwater makes up about 35 times the amount of fresh water in lakes and streams. Groundwater occurs everywhere beneath Earth's surface, but it's usually restricted to depths less than about 750 meters. The volume of groundwater is the equivalent of a 55-meter thick layer spread over the entire surface of Earth. So there's a lot more than you might suspect. It's important for humankind to find potable water, irrigation industry, and usage in homes. Because it's largely hidden from view, it's often forgotten about and subject to contamination by careless acts by humans. And groundwater's primary agent of chemical weathering and is responsible for the formation of caves and sinkholes. And we'll look at karst topography as we end this. So if we break this down in this type of chart, all water on Earth, when we look at unusable, it's about 99%. So we're really only fighting to figure out how to access the 1%. And the water that's usable by humans, 99% of that comes from groundwater. And you'll see that less than 1%, or about 1%, is from lakes and rivers. So here's a graphic we're going to be looking at. And we're going to pay attention to some terms here. This is a picture you should have in your binder. We've got this unsaturated zone, meaning it's not always housing water. But then we're going to find this water table. The water table is a zone in which we are going to see that would fluctuate. And beneath the water table is going to be the saturated zone. This is the location of where we find our groundwater. So before we move on here, we'll pay attention to the spaces here in just a few minutes. But let's just get kind of a general picture of what's taking place beneath the surface. So here's another cross-section profile here. So we'll look at pumping wells. These are what pull on the essentially remove the groundwater and make it serve our purposes for humankind. So groundwater is a resource that humans rely on. Life is dependent on fresh water. So ocean water is not really a viable source for ingesting. Well, aquifers are bodies of water, bodies of rock or soil that actually house the fresh water. We simply build wells to tap into this resource. So if we look at this picture here, we find that if we are pulling this water up to access it, it's actually creating a pressure gradient that groundwater is then flowing to. So we can thus affect the water table. In general, when you pull so much water out and the water table sinks below your well depth, you have essentially the phrase, the well runs dry. I want you to see here, this label right here is a confining unit. This is an impermeable layer. In other words, water cannot infiltrate through it. So in other words, when you have these confining units, water simply just builds up. And we simply find that water, the aquifer, and we just tap into it. A class lab activity that we've either done or will do, we're going to time how long it takes for water to essentially infiltrate or pass through. We'll look at large or coarse sediment, a little bit finer sediment. This is just coarse sand. There's just larger sand grains, fine sand grains, and we'll be adding a letter E to this. It'll be silt and clay. And we're going to time how long it takes for water to infiltrate through. Think of it this way. The coarser the larger the sedimentary particles, the faster water can infiltrate through the substrate. Whereas these sediments are the substrate. When we pour water into the sediment, we'll find that finer, smaller sediment impedes water infiltration due to the very, very small pore spaces. And we'll sort out what this pore space is here in this lecture. And the relevance. Well, our local soils in northeastern Illinois and kind of the Chicagoland suburbs is composed of silt and clay, very fine sediment. So when we get heavy rains, water runs off the surface. It cannot infiltrate into the soil. And here's a picture from class. We'll be looking at the 5 different types. We'll be looking at, let's just say, different sediment, and we'll be running water through them. We're going to time how long it takes. So here's a little picture we'll be seeing in the near future. So we're going to be exploring the concept of porosity and permeability. That sediments and sedimentary rock have a porosity depending on their grain size, the shape, the degree of sorting, and the degree of cementation. So if I look at this picture here, these would be coarse rounded, and they would have particles. This is the sediment itself. And these are going to have large pore spaces, right? So well-sorted coarse-grained sediments usually have a higher porosity than fine-grained sediments because the grains do not fit very well together, right? These larger pore spaces. Over here we see poorly sorted, meaning they're not homogeneous. It's a heterogeneous mixture. Here we have large, we have mid-size, we have small. That in this case here, these generally have a lower porosity because the fine-grained fragments tend to fill in the open spaces, and that's what we see here. So, and to the left here, since sediments tend to fill in the pore space, highly cemented sedimentary rocks have a lower porosity. So you don't have these pore spaces, so these can actually be confining layers. They become impervious sediment. So here we can look at permeability. It's simply a measure of the degree to which the pore spaces are interconnected, and that's the key here, and the size of those interconnections. Low porosity results in low permeability, but high porosity doesn't necessarily imply high permeability. And there are examples of where if you don't have connections or large-sized connections, you can actually have a high porosity but a low permeability. We'll explore that a little bit later. A thin layer of water will always be attracted to mineral grains due to the ionic charge of the surface of the sediment. Water, a polar molecule, can adhere to many substances, including sediment. This is called the force of molecular attraction. Thus, coarse-grained rocks are usually more permeable than fine-grained rocks, and sands are more permeable than clays or anything that's fine-grained. And here's what we're looking at. Water is going to adhere to the sediment, and this is the molecular attraction. It's simply going to hold on. So water has both adhesive properties and cohesive properties. It's going to hold on to itself as well. So that can slow down the permeability as well of groundwater. So let's make sense of this picture now. So we have an unsaturated zone. We have our water table that simply divides the unsaturated to the saturated zone. And this is where we find our groundwater. So if I looked at this picture right here, water that's not groundwater can be held by molecular attraction. Right? In this case, it surrounds the surfaces of rock particles. If this is the water level right here, right? So here's our water table. This is where we're going to find the zone beneath it, where you're going to have all of these openings completely full. Notice above it, this is your unsaturated zone. Water is simply infiltrating through. And over here, this is a picture of gravel. The water level up above here, sometimes you're going to get water. You're going to get pockets of water if it can't infiltrate through. But in general, beneath here, we're talking down here, this here happens to be your saturated zone, and over here is your saturated zone. So this is what's called creviced rocks. So some rocks just have breaks and fractures in them. Whereas soils and other types of aquifers, let's just say they're made up of sediment that's kind of compacted and stuck together. So rock that has pore spaces is different than sediment that is essentially congregating together. So now we can look at what's called karst topography, or making of a sinkhole. Sinkholes are the result of land collapsing onto a cavern that formed from water dissolving a type of rock called limestone. So down here's a picture. So we have a cross-section profile, and here's a pumping well. If it's pulling water, you're having water flow. Groundwater flows. It's moving. And what happens here is you can actually, the groundwater can dissolve limestone and creates these caverns. And at some point, when the weight of the overlying land is greater than the support weight of the cavern, it simply collapses. And that's simply what we're looking at here. Sinkholes are very common to Florida, and they're these features that we get and we find. And we can even find them locally in Illinois. So here's a picture. Florida's pretty much is notorious for getting sinkholes. They make the news relatively regularly. But they're literally just that. They simply create these circular patterns. And we can look at why here. It's called karst topography, and this is it's really the result of the limestone bedrock. That karst topography is a landscape formed from the dissolving process of soluble rocks. Generally it's limestone, but can also be dolostone and gypsum. It's characterized by underground drainage systems such as sinkholes and caves. So what happens is that you get this water flow, and it just creates a spacing, and in the land above it just falls in, and that's just what it calls a sinkhole, right? It's the land sinks into itself, and you can kind of see this right here, and it just forms literally this circular shape. It's a cavern falling in on itself. So finally, the last bit of this is we're looking at karst topography in the United States. Florida is notorious for it, but we are actually located in a region here to where we can actually have karst features, and there are sinkholes that take place on occasion. Not quite as the scale of Florida, but they can happen nonetheless. There you have it, folks.